Hey guys, welcome back to Consistent Code. So today's problem of the day is number of ways to arrive at destination. So I'll quickly explain the problem. Basically, we are having n cities and they are connected by m roads, and then we are given roads in the form of edges. So we need to find the minimum time which the road from which you can reach from road 0 to road n minus 1. For example, if I depict this example to you visually, then basically what the question is asking is that you are at this node 0. Let me mark. So you are at node 0 and you need to reach this node 6 or city 6. So these in the green color I have written the time which will be taken to reach from city 0 to city 4, or from city 4 to city 0, similarly from city 0 to city 6, and from city 6 to city 0. So these numbers in the green color are the time which will be taken to between if we take the road between those two cities. So first of all, what we can do, we can store the roads in the form of a graph. So we'll create an adjacency list of n nodes, and we will also okay. And one more thing, this is a standard problem that we need to find the minimum time to. Uh, this is actually reach. I've written it wrong. So, but you can understand this is reach and minus 1 city from city 0. So basically we will be using Dijkstra's algorithm and we will be modifying it a little bit. So from Dijkstra's algorithm we can find the shortest path from the city, and in this case basically the path has been we have to find the path only, but instead of the edge weight we are given the time. So the problem is same only like Dijkstra algorithm, but in this from the Dijkstra algorithm we can find the shortest path, but we need to find how many shortest path are there in which we take this minimum time. So we will modify the extra algorithm a little bit. So initially what we will do, we will as usual put our initial city 0 into the priority queue. uh, so the first element in the we will put a pair in the priority queue, and the first part of the pair will be the time taken to reach that city, and this will be the city. So we took 0 time to reach the city 0 because initially we are at city 0 only, so hence we have marked the distance also 0. Then we can move to the adjacent cities. So first we can go to city 1, and then we can check that if the time initially for all the cities, the time will be infinite, that is int max. In this code we can write like int max, the distance for all the cities was int max. We store the graph in the from the edges, and then we made a variable count to count the number of paths from which we can reach the n minus 1 city in minimum time. And then we pushed priority 0 comma 0 in a priority queue, that is we are at city 0 and we took 0 time to reach there. And also we marked the distance, the minimum distance, or you can say the minimum time to reach city as 0. Now we will be running a while the priority queue is not empty. So what we are going to do in that, first of all, we will be taking the top element of priority queue. So initially we have only 0, so we will um, take now we will remove this element, and we will check what is the node value of this priority queue. So basically we find that 0 is the node value. So I can say that currently node is 0 or my city is 0. I will check all the adjacent cities. So I will check 4, 1 and 6. So I will just push all the cities into the priority queue if the distance currently, which is maximum, uh, let's say all these distance are infinity. So I hope you will understand. All these are infinity. So all these are infinity. So we will check if the distance now from 0 to 4. Like in this case, that will be in what is the distance to reach the zeroth node? It was 0 because we are standing here. And so what will be the distance to reach the this node? That will be the first element. This is 0. What was the 0? This was 0. The 0 was the distance which we took to reach that node. So this distance was 0. So what will be the time, or you can say distance, to reach node 4 from here? That will be the distance which we took to reach this node plus the distance which will take by using this node. So that will be d plus. So the distance will be the d. Suppose here it was d was 0, then 0 is 5. That will be the minimum distance to reach from 0 to 4 as of now. So now we can see if 0 plus 5 is less than the value of distance, the minimum distance which we are storing in the distance array. So now initially the distance at 4 is infinity. So d plus 5, that will be equals to 0, is obviously less than, sorry, that will be 5, is obviously less than infinity. So what we can do, we can simply mark that at 4 we are having a better distance which is less than infinity, and we will mark this distance 5. And what will we do after that? Now that we have marked its distance, we will also push this node 4 into our priority queue. So we will be pushing this node into our priority queue. So now we will have, and also we will remove, sorry, not we have to remove this 0 comma 0, because we have visited this 0, but we will remove this. And yes, we have already removed this, and we are traversing all of its adjacent cities currently. So first we traverse to 4, and now we are adding this 4 in our priority queue. So now we have added the distance, and what will be the distance which we add? D plus 5. So d plus 5 would be 5. 0 plus 5 was 5, and then will be the city. So the city is 4. And similarly, we can add the rest of the cities in the priority queue. So now we will also add this adjacent cities of 0, which is 6 and then 1. So when we will add these cities, then our priority queue would look something like this. Since it is a minimum priority queue, so when I will add the last element, which is this first node, and the distance was 2, so 2 comma 1, then this will stay at top because this is a minimum priority queue. And now once we are done with the 0th node, we will um, now we will again keep on looping through the this until the priority queue is not empty. Now we will check the top element of the priority queue again. Now the top element is 2 comma 1. So what we will do, we will first of all remove this from the priority queue, and after that we will also uh, and one more thing which I need to tell you, that before removing this, in the previous step only, when we added these elements in the priority queue, we also need to mark their distances, because we added them only if the distance in the distance array was more than what we are getting now when we added them. So we will mark the first node with the minimum distance as 2, and similarly we can mark the this, distance in node 4 as, and one more thing, this has got to be, there's a mistake here, that it will be 7 comma 6. So let me just correct it. So this is 6, and here I need to mark at the sixth position. This tells us minimum distance as 7, so forth. Now if in the next iterations we find distance less than this, then only we will replace these distances, and otherwise we will not be replacing these distances. So now we can see that we are done with the zeroth node. Now we are at the top node, which is 2 comma 1. That is the now we are at the city 1. So first we will remove the city, and that means now we are at this city. So what we will do, we will again check its adjacent cities. So first we will check this city. Its one adjacent city is 0. So but and we also need to check how much distance we will take, or the time we will take to reach 0 if we go after 1. So that will be the time we taken for 1, which was 2, I believe. So yeah, it was 2. So the time will be 2 plus the time taken for this road, that will be 4. So we are getting the time. I'm saying that as d as 4 now for 0. So we will now check in this distance array that the time for 4 is, sorry, not time for 4, time for 0, because we are going to 0th city. So time for 0th city is 0. So this time which we are getting now is greater than the time which we have already got. So we will simply uh, we will not add any of its we will not add the 0 again, and we will discard this move, right? So now we will check the next adjacent city. So the next adjacent city will be 3. Now we will check that what is the time we are taking. So let's say the time now will be the time which we took to reach 1, which is 2, plus the time which will be taken by this road, that will be 3, and that is equals to 5. And initial now currently the time to reach 3 is infinity, and now we are getting time which is smaller than infinity. So what we will do, we will simply mark that we will take the smaller time. So here I can say for 3 the minimum time now is 5, and we can uh, remove this part. So we are, so since we added this time, that is we are getting time which is less than the previous time, we will add this 3, city 3, into our priority queue. So to do that, for doing that, what we will do, we will create a pair for the time which it took. The time is 5, and the city, that is 4, and this will be added to our minimum priority queue. And since it is a minimum priority queue, this element should take the place at the top, right? So now that we are done with the city 3, we will go to the next adjacent city for this uh, city 1. So the next adjacent city is 2, right? So now we will again check for 2. The time taken will be, let's say, t equals to the time taken for reaching 1, which was 2, and the time taken through road is 3. Hence the time is 5, and which is less than the time for 2, which is infinity. So we will again create a pair for this, and also mark in the distance array the minimum time for this city 2. And now we will just create a pair and store that in a priority queue. So the time is 5, and the city is 2. So this will be the place in our priority queue. And now that we have traversed all the adjacent cities for this first city, so we can now again pick the next top element of the priority queue, and that element is 5 comma 2. So now we are at this city 2. Now we will check all its adjacent cities. So now when we will check for 1, then we will, you can see this for yourself, that we will get a distance greater because we came from 1 to 2, and if we will go again to 1, that will obviously, then the time will always be greater than the previous time. Hence we will not be considering this one. So we will go to the next adjacent city, that is 5. So here the time will be the time which we taken for reaching 2, which was 5. So d will be equals to 5 plus the time taken by this road 1, which is 6. Now for reaching 5, the time was infinity, and now we are getting a time 6, which is less than infinity. So we will mark this time as 6, and we will again create a pair to store this city. The city will be 5 and the time taken is 6. So that will be like this pair, 6 comma city is 5. But where will this pair be stored in our priority queue? We need to decide that, and that will be decided because this is a minimum priority queue. These 5, the pairs which are having 5 will be on top, and this element will be below this one. So wait a minute. So we will get something like this in our priority queue. Now that we have traversed all the adjacent cities for the second city, now we will go to the next top element, which is 5 and 2. So we are at city 2 now. Sorry, not at city 2. Actually, we should have deleted this city 2, and so I forgot remove this, removing this second city. So the top element will be 5 and 3. So now we are at city 3. We are here. So what we will do, we will again check for the adjacent elements. So again, if you will see, if you go from city 3 to 1, then your time will be greater than the previous time, because we have came from 1 to 3 previously. So we will not be going to 1, and then we will check for next adjacent city, which will be 6. Now for 6, if we consider the time, it is 7. So now if you will see, the time for reaching 3 is 5, right? And now if you will take this road, the time will be d equals to 5 plus 3, that will be 8, which is obviously greater than the time which we reached, which in which we reached 6 before. The time in which we reached, the minimum time in which we reached 6 was 7, and now we are getting the time from this path as 8. So this we cannot choose this path, hence we will move to the next path, which is from 5, from 3 to 5, right? So now you will see that the again the distance or the time d will be equals to the time for 3, which was 5, and plus 1, so that is 6. And 5 plus 1 is 6, and we have already reached 5 before in time 6. So since this is equal to the minimum time, we can consider this pair. So we will be pushing this pair, and the pair will be 6 comma 5, right? And since this is already present in the priority queue, we just need to create one more pair. So this will be placed here in the priority queue. Now we will again consider the top element. And sorry, the top element was 5 3, which we are done with. So now we will consider this next element, which is 5 comma 4. That means we are at city 4 here. So now we will be traversing to the adjacent cities. So again, you can see, we will, if we will go to 0, then the time will be greater than the minimum time which we have stored in the distance array. So we will moving to the next city. So if we move to 6, then the time is 7. So we can obviously consider this option because the time to reach there now is the time which we took for 4, that is 5, and plus this 2, so that is 7, and the minimum time to reach 6 was 7, and since this is equals to minimum time, we can simply create a pair that the time is 7 and we are reaching 6, and we can place this element in our priority queue. So this will be placed here in our priority queue, right? Let me reduce its length. So now this will be the situation, and then there are no other adjacent elements for 4. So now we are done with this 4 and we will remove this node. So and now we will again consider this top element 5 comma 6. So from here we can go to 2, but if you will see, if you go to 2, you will get a distance which or the time greater than the previous time to reach 2. If you will go from 5 to 3, you will again find the time greater than the previous time to reach 3. So if you will go to 6, you will find the time as 7, which is the minimum time before. So we can consider this pair, and we will make a pair of 7 comma 6, and we will place this in our priority queue. So we will have this pair once more. So this will be placed here in our priority queue. So now we are done with all adjacent elements of this city 5. So we will remove this, and we are having this city again now. So we will again do the same thing, and this will be removed, and one more 7 comma 6 will be added. So again this same 7 comma 6 will be added. uh, it is it will be added here. Now we will again consider the top element, and now when the city is 6, which is the destination, what we will do, we will say that since we have reached the destination, and the distance which is 7 is also the minimum distance in our distance array, so this is a valid path. So we can just say in our suppose the answer was 0, so we will increment our answer by 1, and we will take the mod m, because we need to answer the output the answer in modulo m, and the m, what is the value of value of m, that is 1 10 to the power 9 plus 7. We have already taken constant m equals to this in our code. So now you can see similarly, since they, and now we will not be traversing to the adjacent cities of 6 because this is the destination. So we will just remove this element from our priority queue, like so this will be removed. And similarly, when we will go to the next element, that is also the destination, so answer will be again incremented by 1, and we will take a mod m. So when all of them will be removed, because all of them are destination, our priority queue will become empty, and my answer will become 4. So we'll get the answer as 4. And now since our priority queue will be empty, we will end the loop. So this is how we will get our answer. Now I hope you got understood the explanation. Now I will explain the code to you. So first we created the priority queue. We created a variable count, which in this I created answer, but here I am considering the variable as count to store my number of paths in minimum time. So first what we did, we pushed the source with which is 0, and what would be the time to reach source, that will obviously be 0. And also we mark the distance, minimum distance to reach 0 as 0 because we are standing there only. Now we will start our loop until priority queue is not empty. And this is what we did in our explanation. First, we will take the top element. We took the top element here. We will remove it, but we have stored this top element in a variable. Now, so the top value city will be this node. This node means the city. And what will the distance taken to reach that city so far? That will be this value d. So now we will check if this is the destination. What we will do, we will increment the count by 1 and we will continue the loop to the next part. And but if this is not the destination, what we will do? Uh, we will simply be uh, you know adding moving to the adjacent cities. So in this element, we are considering the adjacent cities as the child, and we are moving to the adjacent cities of this current city, and we are checking if the distance from our current city and and then we are adding the time to move to the adjacent city is less than the time stored in distance array, and we are getting a shorter path. And in that case, we are updating the distance array, and we are also pushing those elements back in a priority queue. And when this loop will end, we will be having our count stored in our count variable. So now let me just show you by submitting this code. Okay, wait. So my internet connection was not working, so let me submit this again. And we have solved the problem successfully. So if you like the explanation, make sure you hit the like button and subscribe to the channel. And I will see you tomorrow with the next problem of the